Hello everyone, and I'd like to thank everyone for their attention to our research. In this presentation, I'm going to talk about our proposed curvature controllable waterjet steerable needles, and will show that duty cycling of the waterjet will improve the radius of curvature and thus the steerability of these new steerable needles. Needles are awesome medical instruments, but inflexible needles often cannot reach to targets in difficult anatomical places. Thus, the need arises for flexible needles that can be steered around the anatomical obstacles. Robotic needle steering allows for insertion of long, flexible needles along curved and controlled paths, steering around obstacles through soft tissue to reach the target. Moreover, multiple targets can be reached from a single insertion. In most needle steering methods proposed in the literature, curvature is created using an asymmetric force at the tip of the needle. Traditionally, this has been accomplished through bevel tips or pre-curved sections. Radius of curvature can only be controlled for a given tissue-needle combination using complex methods such as manipulating the tissue via external forces and rotational duty cycling that can only decrease the curvature, and the maximum curvature is still dependent on the needle tissue selection. Other limitations of conventional steerable needles are large radii of curvature, especially in very soft tissues. Restricted reachable workspace because of large radii of curvatures. Torsional friction because of rotational duty cycling. Continuous rotation can also cause a spiral track in the soft tissue, causing more tissue damage. The buckling issue. And a large diameter of the needle that increases the risk of complication of patients' discomfort. Therefore, developing new techniques that can compensate for some of the listed issues and moves the steerable needles towards their clinical acceptance seems to be very important. We have proposed a new class of steerable needles that we call Waterjet Steerable needles that can address some of the limitations of the traditional steerable needles discussed before. Specifically, the curvature can be controlled from 0 to maximum curvature by duty cycling a waterjet. In this type of steerable needles, the direction of the tissue fracture is controlled by high-velocity waterjet coming out of a sub-millimeter angled nozzle, and then the flexible needle follows. This process continues until the needle is steered to the target point. In our previous research, we have shown that the waterjet reduces the tip forces reflected back to the base of the needle, and this gives the advantage of no buckling insertion while steering with waterjet. Furthermore, since the curvature is controlled without rotational duty cycling, the torsional friction is prevented too. This figure shows the CAD model of the waterjet needle that consists of an idler tube with sub-millimeter diameter soldered to a copper tubing which is connected to the waterjet nozzle, and then PEEK tubing. In order to be able to steer, we need an angled nozzle so that the waterjet cuts a pass in a certain angle, after which is followed by the flexible needle. Continuing this process causes the needle to steer. These figures show the waterjet fixed angle tip used in our experiments. And this is the final experimental setup that we used in our experiments. Unlike conventional steerable needles that have constant curvature, we can control the curvature of the waterjet steerable needle by waterjet duty cycling. 0% duty cycling means that the waterjet is turned off for the entire length of insertion, and 100 duty cycling means that the waterjet is on in the whole length of insertion. The kinematic model of the waterjet steerable needle consists of two parts. The step lengths can be predicted by the cut depths model of the waterjet soft tissue interaction that was obtained in our other journal paper, and it's just summarized here. The cut depth is a function of waterjet properties such as velocity and diameter, as well as the mechanical properties of the soft tissue being penetrated. These mechanical properties are constitutive response and fracture toughness. And the second part is a kinematic model to describe the needle paths. This is an adaptation of the bicycle model, the famous bicycle model for steerable needles. In this slide and the next slide, the results of the curvature control of the waterjet needle is shown. This figure shows the curvature control of the waterjet needle by waterjet duty cycling in SEBS soft tissue simulants. The best radius of curvature here is around 49 millimeter. And this shows the results of the curvature control in 10% gelatin tissues. The stiffness of this tissue is comparable to the stiffness of the healthy liver, so it's very soft. The best curvature of 70 millimeter is obtained in this tissue. You can also see that the kinematic model can accurately fit our experimental results. This table presents a comparison of the smallest radius of curvature obtained with waterjet steerable needle and some of the conventional steerable needles in the literature in the same soft tissue phantom. Flexure-based and bent-tip steerable needles are known to have the smallest radius of curvature in the literature. But you can see that in gelatin soft tissue, the best radius of curvature of the waterjet steerable needle is smaller than the radius of curvature of these needles without lots of tissue damage that is associated with these steerable needles. This promises a better method for curvature control and steerability in comparison to the steerable needles in the literature. Another interesting result from the waterjet duty cycling experiment is that, as you can see from these figures, curvature of the waterjet steerable needle is a linear function of the duty cycling of the waterjet, and this gives us the freedom to find the curvature based on what duty cycling we are using for waterjet. Thanks for your attention. I hope you enjoyed our research on waterjet steerable needles.